Hi everyone, I'm Shen Zhu from Nanyang Technological University, Singapore. I am presenting my work co-authored with Shiqing Li and Dr. Weichen Liu. iMAD, an in-memory accelerator for AdderNet with efficient 8-bit addition and subtraction operations. Convolutional neural networks are widely adopted in computer vision applications. Instead of deployed on the cloud, they are usually deployed on the edge to achieve good privacy and reduce the overall latency by removing the network transfer between the edge and the cloud. But CNN inference on the edge also has some challenges. First, on the software side, CNNs are memory intensive and computational intensive. Taking GoogleNet as an example, modern CNNs are very deep, and they use floating point 32-bit parameters, resulting in a large model size. Taking a look at the convolution layer, we find that the convolution is made up of iterative multiplication and accumulation operations. The numerous multiplications bring high computation cost. The large model size and the high computation cost are two main challenges on the software side. Second, on the hardware side, the edge devices rely on traditional CPU-GPU architectures. Traditional architectures have heavy data movement between the disk, memory, and the processing units. The data movement between different chips brings the memory problem, and the heavy data movement brings high energy cost. Therefore, we need not only more efficient CNNs, but also more efficient hardware architectures. To reduce the computation overhead, AdderNet replaces the multiplication in CNNs with lightweight addition-subtraction operations. Traditional CNNs use L2 norm to measure the feature similarity. AdderNet uses L1 norm. As the equations show below, AdderNet only contains subtractions and additions. Thanks to the less arithmetic complexity, AdderNet can bring faster speed and lower power. Compared with using 32-bit values, using 8-bit integers can remain high accuracy and bring 4 times smaller model size and memory usage. Therefore, the quantized AdderNet can serve the challenges of traditional CNNs on the software side. On the hardware side, to reduce the data movement between memory and the processing units, researchers put the memory and the processing units on the same chip. This is named as near-memory computing. It reduces the data transfer overhead, but it does not reduce the data movement. Therefore, in-memory computing is proposed. The non-volatile memory can work as both the storage and the memory. We can build a computational memory arrays based on non-volatile memory to processing where the data locates. In-memory computing reduces the data movement greatly and brings high energy efficiency. Instead of parallel processing across the cores, now we can conduct parallel processing across the data, which brings very high parallelism. Therefore, we propose an in-memory accelerator for AdderNet, named iMAD. We target the quantized AdderNet instead of traditional full procession CNNs, and adopt in-memory computing instead of traditional hardware architecture. Our contributions include the circuit and operator level by proposing enhanced sensing circuits and co-optimizing the addition and subtraction operations. Upon the circuit and operator, we build the accelerator architecture and propose an optimized AdderNet solution for our in-memory computing platform. The first challenge we met is the inefficient in-memory subtraction. Existing works achieve subtraction by one NOT and one ADD, which has long latency. Adding a dedicated subtraction logic to the sensing circuit can reduce the subtraction latency. but the addition performance is reduced due to the add-on circuits. The add-on circuits also bring higher power and larger area, because both addition and subtraction counts in AdderNet. So we propose to co-optimize them in this paper. As a result, we achieve better addition and subtraction performance without increasing the power and the area. Before we go into the details, let's have a quick review of the background. This slide shows how STT-MRAM-based in-memory computing works. Standard STT-MRAM cells contains a magnetic tunnel junction and an access transistor. The MTG can be viewed as a variable resistor storing 0 or 1. Applying a reference current to two memory cells, you can get a sensed voltage inside the sense amplifier at the bottom. The sensed voltage has three cases: V00, V01, and V11. Comparing the sense voltage with reference voltage V-end, we can get the end result. Comparing V-sense with V-OR, we can get the OR result. We can add more logic gates to achieve more complex functions like addition and subtraction. As the Boolean equations show, sum is the addition result, diff is the subtraction result. Sum and diff can share the same circuit, but carry and borrow need their own circuit. The graph shows on the right, the direct implementation results in 5 logic gates to generate the carry and the borrow. To reduce the overhead, we propose to co-optimize the addition and subtraction logic. Through Boolean equation transformation, we obtain the following equations on carry and borrow generation. As the circuit shows on the right, now we only need 2 multiplexers instead of 5 logic gates. The proposed method is more area efficient. This graph shows the detailed addition workflow. We add the numbers bit by bit. For example, A and B are 2 vectors. Y is the addition result vector. First, we read in 1 bit of A and B, and the sense amplifier calculates sum and carry. We store the sum to the result cells, and the carry to a latch stay inside the sense amplifier. We repeat this process for n times to finish the n-bit addition. The carry latch is initialized at 0. It stores the carry from this cycle and provides it in the next cycle as the carry in. Similarly, we conduct bit-by-bit subtraction. Because B is needed to generate the borrow, we read in B first, and then read in A and B together to calculate the diff and borrow. The diff is stored into the memory. The borrow is also stored in the latch C to be used as the borrow E in the next cycle. This example shows that our accelerator can conduct signed integer arithmetics, and the computation is parallel among columns. This graph shows the details of our sense amplifier. It can conduct 7 functions with the configurations in this table. With only 4 output selector ports, we can reduce the size of the selector. As the carry and borrow are only used in the next cycle, slower carry and borrow generation is acceptable. So we use transmission gate-based multiplexers, which has fewer transistors than other multiplexers. Also, the carry and borrow share the same selector signal XOR, so that we can reduce one-off logic inside the multiplexers. Based on the proposed circuit, we build the accelerator architecture. It contains 2 main components: the computing memory arrays and the digital processing unit. As there are many computing memory arrays, we can conduct parallel processing across arrays. Inside the computing memory array, each column has a sense amplifier. Thus, we can conduct parallel processing across columns inside each array. The overall workflow is shown in the left. The weights are loaded into the computing memory arrays before inference, and we only need to mapping the activations at runtime. Thus, we have good weight reuse. After mapping the activations, we conduct parallel convolution in the computing memory arrays. We send the convolution results to the digital processing unit for activation function and batch normalization. However, we encounter another challenge when executing the AdderNet convolution. The original AdderNet has one sum, one absolute function, and one addition in the innermost loop. It is efficient on CPU and GPU, but it is not efficient on in-memory computing platforms because subtraction has longer latency than addition. So the first question is, can we replace these subtractions with additions? Also, the absolute function has no efficient implementation on the in-memory platform. The second question is, can we fuse the absolute function with the accumulation? Following this logic, we propose the optimized AdderNet convolution algorithm for our in-memory accelerator. Because the filter weights are known before inference, we can use their offset values. Thus, the subtraction between the weights and the activation is replaced by addition. Further, we fuse the absolute function with the subtraction. It results in a negative function. We fuse the negative function with the accumulation, so that we only need to subtract the positive numbers and add the negative numbers. Therefore, the operations at one output point is shown in the equations below. The proposed new algorithm only has two operations in the innermost loop, because the summation of alpha and beta is 1. Next, let's see how we map the optimized convolution algorithm to our accelerator. We conduct an image-to-column transformation to transform the direct convolution into a matrix multiplication problem. This is very common on CPU and GPU because image-to-column decouples the data dependency and improves the parallelism. We map the weights and the activations to the memory array in pairs. We add these weight activation pairs together, then conduct the fused negative accumulation on the immediate results. We only need to go through the data twice, so this mapping is very efficient. Now I have presented the accelerator architecture and the optimized algorithm. Let us see the evaluation results. We implemented the proposed circuit and the related works in the same 45nm process. This graph shows the normalized 8-bit subtraction performance and the normalized sense amplifier area. Adding the subtraction logic to existing designs brings large area and higher power. Our comb-optimized addition and subtraction logic can reduce the area by 26% and reduce the power by 20%. Compared with existing works, our proposed iMAD can reduce the latency by 49% and reduce the energy by 48%. We also care about the addition performance. It is obvious that adding the subtraction logic to existing designs brings higher overhead and reduces the efficiency. In contrast, our proposed co-optimized logic can achieve better addition performance along with subtraction function. We can achieve 33% higher efficiency than existing works. The operator level performance contributes to the layer level performance. So we evaluated the layer level performance on elevator layers. We choose 4 layers with different sizes, ranging from 500 to 4,000. We observe similar performance gains among different sizes. As the graphs on the right show, our circuit and architecture provides about 60% speed up and energy efficiency, while the proposed optimized AdderNet convolution algorithm contributes another 40% speed up and energy efficiency. The layer level performance is related to alpha and beta, as beta reflects how much subtractions in the absolute function are replaced by addition. We conduct one more case study on how the layer level speed up and energy efficiency change with beta. As the graph shows below, our accelerator achieves higher speed up and energy efficiency with the optimized AdderNet convolution. And the larger the beta, the higher the speed up and energy efficiency. In conclusion, we have built an in-memory accelerator for AdderNet. We realized the more efficient addition and subtraction operations by co-optimizing the equations and simplifying the circuits. We have achieved the more efficient AdderNet convolution by replacing the inefficient subtractions with additions and fusing operators. Evaluation results show that our proposed methods are effective. This is the reference for this presentation. Thank you.